He knows a lot about the science stuff. Professor Dave explains.
Over the two previous tutorials, we examined our first quantum problem, that of the particle in a box. This involved solving the time-independent Schrodinger equation for a quantum particle in an infinite square well. Now it's time to take what we learned there and apply it to another scenario. This time we will examine a quantum particle which encounters a barrier. This is a rough model that can be used to describe an electron which finds a defect as it travels through a wire. If this defect is at a different potential than the rest of the wire, it will cause a potential barrier. We already know that a particle will tend to reside in regions of lower potential. Objects fall to lower gravitational potential. Charged particles move to regions of lower electrical potential, and so forth. So to apply that to this situation, imagine that a particle is traveling in a region where the potential, V, equals 0, and it possesses an energy, E, of 0.5. Then it encounters the barrier, which has a potential equal to 1. If this is a classical particle, we can conclude that it does not have sufficient energy to surpass the barrier, and it will bounce back. Instead, if its energy was equal to 2, it could sail right over this barrier and would only have its motion disrupted if it encountered a region with a potential that is larger than its energy. However, if this is a quantum particle, it will behave much differently, because these are both particles and waves, and thus their behavior when encountering a barrier will exhibit both particle-like and wave-like characteristics. To see exactly what happens at the barrier, we will once again have to solve the Schrodinger equation. To keep things simple, we will examine a one-dimensional problem and use the one-dimensional time-independent Schrodinger equation. While this keeps the math more manageable, we must also realize that our results will only be an approximation of our physical reality, which is three-dimensional and time-dependent. Now, let's quickly recall that when we were looking at the particle in a box, the particle was trapped between two infinite barriers. The difference now is that we are considering a singular, finite energy barrier, which we can refer to as V0. So to describe the potential in any location for our system, we can use the following set of equations. First, V of x equals V0 when x is between 0 and a inclusive. And V of x equals 0 when x is less than 0 or greater than a, which is just everywhere else. In other words, the energy barrier spans from 0 to a. Now on this graph, the vertical axis represents energy, so we can see that the energy of the particle will determine whether it will encounter the barrier. If the particle has an energy that is much greater than V0, it will not encounter the barrier, it will pass right over it. And if it has an energy that is much smaller than V0, it will indeed encounter the barrier. Just to be as clear as possible, let's identify three regions on the diagram and label them A, B, and C. A is the section approaching the barrier. B is the section spanning the barrier. C is the section after the barrier, and any particle can have an energy that is greater than or less than V0. So the main difference here is that when we were looking at the particle in a box, the potential was infinity on either side of the well. But now we are looking at a barrier that represents a potential which is not infinite. This means that a quantum particle with enough energy, an energy larger than V0, can cross to the other side of the barrier, almost like jumping over a fence. But the much more interesting situation arises when the particle has an energy that is less than V0. If we were thinking strictly classically, we would conclude that the particle will not be able to surpass the barrier, as it does not have enough energy. We would expect that such a particle would strike the barrier and be reflected, or essentially bounce back, and we would say that there is a 0 probability that the particle would be transmitted through the barrier. But in the quantum world, there is some non-zero probability that a particle with energy less than V0 can still cross the barrier. This phenomenon is referred to as quantum tunneling. Quantum tunneling is something that is very difficult for our classically trained minds to grasp. If we were bouncing a tennis ball against the bedroom wall, and it suddenly passed through the wall to end up in the next room over, we would certainly be shocked. We expect that the ball will perpetually bounce off the wall, or reflect. This is what our intuition tells us must happen. But due to the wave nature of matter on the quantum level, there is indeed some probability that a quantum particle can traverse such a barrier. By the same token, if we were tossing a tennis ball over some kind of barrier, we would expect that it will always make it to the other side. But in the quantum world, when considering a particle with an energy greater than V0, again there is some non-zero probability that it will be reflected by the barrier, unable to make it over. As this all probably sounds completely insane, let's dive into the math which informs us of these facts. We are going to want to solve the time-independent Schrodinger equation for this system. Luckily, we already have some practice with this, so if you missed the handful of tutorials before this one, make sure to watch those first. Here we will employ precisely the same logic that we should already be familiar with. So to refresh our memory, here is the time-independent Schrodinger equation. We have negative h bar squared over 2m times the second derivative of psi of x with respect to x plus v times psi of x equals energy E times psi of x. Now, just as we did for the particle in a box, we are going to solve this equation by taking into account the specific boundary conditions defined by v of x. And the first few things we will do to manipulate this equation are precisely the same as we did for the particle in the box as well. Let's begin with sections A and C. In these regions, the particle can move freely, and thus can be treated just like the particle in the box, which means that v of x equals 0, and we can get rid of this second term. From here, we will take the same steps as we did for the particle in a box. We want to isolate this second partial derivative, so we can multiply both sides by negative 2m over h bar squared, and then we can introduce the value k, which is equal to root 2me over h bar. Though in this case, we will refer to it as k0, because this time we will have to define more k terms later. This means that k0 squared is 2me over h bar squared, and we can make the relevant substitution. So the right side of the equation becomes negative k0 squared psi. We can move the k term to the other side, and that leaves us with precisely the same second-order differential equation to solve as with the particle in the box. In that tutorial, we simply revealed the solution rather than rigorously solving, so here we will do the same thing, and the only reason we don't get precisely the same solution as with the particle in the box is that the boundary conditions are different. We are not bounded on both sides. In this case, the wave is not rigidly constrained in place. So for general help in solving second-order differential equations, visit the mathematics playlist. Otherwise, we can solve for psi A and psi C, which correspond to regions A and C, and we get the following expressions. So that was fairly straightforward, but now let's move on to the central region B, which will be a bit more complicated. Again, we can start with the time-independent Schrodinger equation, but this time the simplification we made in getting rid of the second term will not be possible, since the particle is not moving freely like it was in the square well. We have a barrier to deal with. The barrier potential is represented by V0, so let's put that in there instead of V of x. Now in this case, we have to be mindful of the particle's energy. If the particle has an energy that is less than V0, the energy is lower than the barrier height, and can thus be thought of as being inside the barrier. Again, this sounds like it should be impossible, but we must always be mindful of the wave-like properties of the particle. Waves can go through walls, be they sound waves or the Wi-Fi you're using right now. A quantum particle can also tunnel through a barrier, and the point of this exercise is to examine what the wave function looks like when it encounters a barrier like this. It won't be like that of a freely traveling wave, because the situation is different, so we have to do some work to find out what it does look like. Mathematically, this means we can't use the same type of functions that we used where the potential was 0, which turned out to be complex exponentials. Now we must use real exponentials. Let's justify this graphically. Here we can see two functions plotted. The first, f of x, is a sum of two real exponentials, e to the x and e to the negative x. The second, g of x, is a sum of two complex exponentials, e to the ix and e to the negative ix. We already know how g of x works because the wave functions we've encountered so far have taken this form. This function describes the behavior of a wave that is stationary and unaltered by a potential. In contrast, f of x is a localized function. It represents a wave that occupies only a narrow domain and then stops abruptly. This is what we will use for the wave function in section B because it is the mathematical representation of a barrier. The particle has some small chance of entering the barrier until reaching some penetration depth. The probability density function will attenuate as the particle's position distribution reaches deeper into the barrier. So to summarize the main takeaway here, when the particle has an energy that is smaller than the height of the barrier, v0, we will use a real exponential, and when the particle has an energy that is larger than the height of the barrier, we will use a complex exponential. Let's first consider the case where e is less than v0, or lower than the barrier height. Here is our equation, and since we can't get rid of the v term this time, let's subtract e times psi of x from both sides, and then simplify by combining these last two terms, giving us the quantity v0 minus e times psi of x. Now from here, we will do almost the same thing as we have done so far, just with a slight adjustment. Let's multiply through by 2m over h bar squared, though positive instead of negative this time, and then define a k value, which this time can be called k below, referring to the set of energies that are below the barrier. This will be equal to root 2m times the quantity v0 minus e over h bar. That means this whole term can be written as simply k below squared times psi of x. And with that substitution, we have a second-order differential equation of precisely the same form as we solved a moment ago. This means we can now write out our solution for the wave function as a linear combination of real exponentials. Since the constants a through d are taken, let's write this as psi b below of x equals f times e to the quantity k below times x, plus g times e to the quantity negative k below times x. Again, this is the only solution that will utilize real exponentials rather than complex exponentials, because it's the only region where the particle cannot travel freely. To finish this off, let's consider the case where e is greater than v0, or higher than the height of the barrier. Here, everything will be the same as what we just saw, but let's use a different constant, k above, which is the same as k below, but instead of v0 minus e, we have e minus v0 in the parenthetical. As we would expect, the resulting wave function that acts as a solution to this differential equation will be a combination of complex exponentials, just like in regions A and C. Requiring new constants, this can be written as psi b above of x equals h times e to the ik above times x, plus k times e to the negative ik above times x. So just to reiterate what we did for region B of this diagram, we used real exponentials inside the barrier because we expect a decay of the wave function and a low value for the probability density function, since this is a barrier. But above the barrier, we used complex exponentials because here we expect a free, non-decaying wave function, just like in the other regions. So to synthesize everything we've done so far, this is the wave function for region A. Now let's split this up into psi right A and psi left A, which represent wave functions in region A which have a part that may travel to the right and left, respectively, where the coefficients A and B describe the relative probabilities of the particle traveling in those directions. So if B equals 0, there is 0 probability of finding the particle traveling to the left, and if A is 0, there is 0 probability of finding the particle traveling to the right. Illustrating the first example mathematically, we drop the b term from psi a of x because that term equals 0, and then write the probability density function psi times psi star. Because the complex exponentials multiply to give e to the 0, or 1, we simply get a squared, which is the mathematical justification of why we can only find the particle traveling to the right. We can do the same thing for region C. Here we found this expression for psi c, and we can split this up into psi right c and psi left c. And then finally for region B, we found that the wave function will be different depending on the energy of the particle. For psi b below, we won't split this up into left and right, as they are real exponentials and thus don't represent a traveling wave. In this scenario, the particle is localized. But for psi b above, we can again split this up and get psi b above right and psi b above left, just like we did for regions A and C. Now that we have everything set up, we are ready to find the solution. Let's consider a particle approaching the barrier from the left-hand side. With this assumption, we can say that the constant d is 0. There can be no wave coming from the right side of the barrier, and there is no way for a wave traveling to the right to reflect once beyond the barrier and come back the other way. So this constant must be 0, meaning that psi left c equals 0. All other constants may have some value, because motion to the right in A, B, and C is implied if the particle surpasses the barrier. Motion to the left in A occurs if the particle reflects, and even motion to the left in B is possible if the particle penetrates the barrier to some degree prior to reflection. So motion to the left in region C is the only motion that is not permitted. So let's look at a particle with an energy that is smaller than V0 by applying the boundary conditions to get the constants as well as the solution to the Schrodinger equation. So just like with the particle in a box, we need to find the conditions under which the wave function and its derivative are continuous over the spatial domain where our problem is defined. The wave function must also be normalizable, meaning that the integral over the relevant domain of the wave function times its conjugate must equal 1. First, let's examine the boundary x equals 0. This is the boundary between regions A and B, and at this position we need for psi A to equal psi B below. By setting these equal to one another at the boundary, we are ensuring the continuity of the wave function over the boundary. Furthermore, we must ensure that the wave function is continuous at the boundary with the barrier in a way that is independent of its energy, such that it describes both a particle surpassing the barrier and a particle being reflected by the barrier. Let's write this out with the full expressions now. Since we are examining x equals 0, let's plug in 0 everywhere we see x. That makes all of these terms e to the 0, and anything raised to the 0 power is 1, so that simplifies this significantly, leaving us with a plus b equals f plus g. Let's label this equation 1. Now we also need their derivatives to be equal at this boundary, because continuous functions must have continuous derivatives. This means that the partial derivative of psi a with respect to x must equal the partial derivative of psi b below with respect to x. Differentiating these expressions will be rather easy. We just pull whatever coefficients are in front of the x in the exponential terms out in front of each term, which leaves us with this expression. Again, we can plug in 0 anywhere we see x, which makes all the e terms go away, leaving us with ik0 a minus ik0 b equals k below f minus k below g. And we can label this equation 2. Now let's examine the other boundary, the one between regions B and C, where x equals a. Here, we need for psi b below to be equal to psi c, again to ensure continuity for the wave function across this boundary. That will give us this expression, and recalling that we determined d to be 0 earlier, we can get rid of this last term. Now, since this boundary has x equal to a, we can plug in a anywhere we see x. This time, these terms won't go away, so we are left with this. Let's label this equation 3. And finally, we need to find the conditions under which the derivatives of psi b below and psi c are continuous at x equals a. So we can take the derivative of this expression and then plug in a for x to get this. This will be equation 4. So altogether, we have solved the Schrodinger equation, and this is the system of 4 equations that we have derived simply by using the boundary conditions of the system and forcing the wave function to be continuous. Now we have only 4 equations, but we have 5 variables, a, b, c, f, and g. This means the system is underdetermined, but in the next tutorial, we will rearrange these equations so as to make them solvable, which will require things called transmission and reflection coefficients. So let's move forward and define these terms so that we can go through the linear algebra required to solve this system of equations, and then interpret the fascinating results, which elucidate the capacity of a quantum particle to tunnel through a potential barrier.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.